Okay, good day everyone. My name is Keyi and from New York University Abu Dhabi. The work I'm going to present is a spatial-temporal planning simulation of temporary elevators in construction using a game engine. Temporary elevator planning means designing a reasonable and efficient system to transport the resources according to project characteristics and team requirements. Because it significantly impacts safety risk, construction productivity, and capital investment. The temporary elevator planning is one of the important tasks in construction projects, especially for high-rise buildings. The content for this plan includes two main aspects. The one is configuration planning, which refers to determine the number, type, and the location of temporary elevators. And the other one is operation planning. It determines the transportation sequence and the motion route. In recent years, the concept of spatial-temporal planning attracts a lot of attention. And it takes the use of both time and space into account to organize and control construction activities, so it can avoid the potential time or space conflicts that lead to various challenges such as safety, quality, delivery, and cost. With this perspective, it's beneficial that the temporary elevator planning considers service data and floors and time and space availability of relevant planning elements seriously. For the temporary elevator spatial temporal planning, this plan, it requires planning elements should be clean, sure, and relevant information are efficiently conveyed. However, current discipline wares are generally abstract, no-dimensional, and static. Even when the 4D model is adopted, the discipline effect of temporary elevator spatial temporal planning is still limited. To address this limitation, this work proposes a spatial temporal planning simulation framework for temporary elevators using a game engine, which consists of 3 steps. In step 1, the data is imported from the BIM model schedule, project schedule, and the planning solutions. The first 2 categories are used to generate the 4D model, and the last one is to determine the planning schemes. In order to classify and organize the data from planning solutions, data model was established, and there are 5 components. The middle one is the temporary elevator specifications, including rated velocity, acceleration, and deceleration. And the 2 left components, service data and the floors, they are used to determine the configuration and planning schemes. And the right ones are transportation task and the motion routes, which are used to determine operation planning schemes. Based on the important data, the spatial temporal planning simulation scheme is generated, which is divided into 2 parts. The first part is configuration simulation scheme. Temporary elevator camps, loading and unloading service floors, as well as their workload and the demand levels are especially involved. The workload level is determined by the total transportation time of a specific cape, and the demand level of floors depends on the quantity of resources loaded or unloaded. In the operation simulation scheme, and aside temporary elevator cape, loading and unloading service floors, as well as their work or use statuses are especially involved. And they are both determined by the time details of transportation task. Regarding the transportation task time calculation for each segment of a task, there has three sub-processes. They are motion time, door operation times, and resource transfer times. If the distance between two stops is more than or equal to the distance for cab to accelerate from 0 to its rated velocity and then decelerate to 0, the time is determined by the first fraction of operation 2. Otherwise, the second fraction is used. And this equation is derived from the acceleration and the deceleration equations, and the condition is that the final velocity at the end of the acceleration equals the final velocity, initial velocity at the beginning of the deceleration. And according to the generated planning schemes, the spatial-temporal planning simulation is conducted in step 3. So considering the complicated relationship between time and space, and the Humes and the values of columns are used to combine the 4D model. In the configuration and simulation, temporary cabs, loading and unloading service floors are marked with corresponding color Humes and the values according to their work and demand levels. In the operation simulation, temporary cabs and loading and unloading service floors with current and other categories are marked with specific column Humes and values according to their work or use statuses. So in the experiment, there were 2 cases to conduct. In the configuration simulation, we can see on different service dates, aside temporary elevator cabs and the corresponding loading and unloading, and their workload and the demand levels were highlighted with specific Humes and values. In the operation simulation, so we can see different steps of transportation task aside cab and its corresponding loading and unloading service floors. Their work and use statuses were highlighted with corresponding colorful Humes and values. So in this research, through a customized display way, various elements are clearly shown and corresponding information is efficiently conveyed. So the spatial-temporal planning simulation is intuitive and convenient. Meanwhile, and the changes in their levels and the statuses can be distinguished and monitored, so which efficiently enhancing the display effect of spatial-temporal planning solutions. Training advice in the virtual environment of realistic situations is beneficial for actual work. So in the future, we are focused on developing a virtual reality training program for the spatial-temporal planning of temporary elevators. So let's all, thank you very much.